So good morning, everybody. So I decided to talk to you not so much about myself and my life, although I will say a bit, but talk about the future of physics. And what I really mean is what we don't know. That's the future. It is always nice to remind ourselves how much we do know. And you, young scientists, have been working very hard for many years to learn everything we do know and to arm yourself with the tools of knowledge in order to do what is truly exciting about science, to explore what we don't know. We do know an immense amount. Science has been extraordinarily successful, especially in the field that I'm going to discuss, which is physics, and with emphasis on fundamental physics. We have learned an amazing amount just in the last 50 years, where we have discovered and understood the basic building blocks of all the matter we have ever seen and the forces that act on them. We've unraveled the structure of matter and confirmed the atomic hypothesis. Matter is made of atoms, but atoms themselves have structure, which within the last century we have understood in extraordinary detail. The structure of atoms, made out of one of the kinds of the elementary constituents of matter, electrons, and the structure of the small nuclei that make up the center of atoms and where the mass of the atom is largely located, which are made up, we understand now, of constituent elementary particles called quarks, which make up the nucleons, neutrons, and protons that sit in the nuclei. In addition to identifying and measuring the properties of the elementary particles in nature, we have understood in great detail the three forces that act on these elementary particles in atoms, in nuclei, namely the force of electromagnetism, which was already understood, of course, in the 19th century, but which in its quantum version explains in great detail and extraordinary precision. Sometimes the precision of our tests of the quantum theory of electromagnetism are accurate to 1 part in 10 billion. And that theory of atomic structure underlies, of course, all of chemistry and the behavior of ordinary materials we see around us. But towards the end of the 20th century, we understood the structure and behavior of the particles that make up the nuclei of atoms, the quarks, which are subject to two other forces. The weak nuclear force that is responsible for the transmutation of elements of radioactivity, and the strong nuclear force, which binds quarks together in atoms and gives rise to the force between nuclei. In the field of astronomy and astrophysics, 100 years ago, that field was completely observational. Today, we have mapped out the entire universe, its history from very early on until today and beyond. And astronomy and even cosmology have become empirical, quantitative sciences where we understand an enormous amount. And in studying the behavior of ordinary matter, we have achieved, using quantum mechanics, an exquisite understanding and increasing control of matter in all of its phases down to the scale of individual atoms, which we are beginning to be able to manipulate at will. But the way I view it, scientists should think of themselves as embedded in a vast ocean of ignorance. Our job, our goal, driven by curiosity, the desire to know and control nature, we push outward into this sea of ignorance. And we are only aware of a small portion of this vast sea of ignorance. Only that part of the sea of ignorance that is on the boundaries of our knowledge. And one of the greatest things, one of the lessons that you will learn from experience as you go on in science is, and you begin to understand new things and make new discoveries and increase our knowledge, you will be faced with the phenomena that the more you learn, the more you realize you don't know. But in fact, that, in my opinion, is one of the most important products of knowledge, ignorance. I don't mean stupid ignorance, the kind of ignorance that leads to bigotry or racism or war, but informed, intelligent ignorance that leads to new questions that are scientific. And what I mean by a scientific question is a well-formulated question that can be answered, can be approached and answered by observation, by measurement, experiment, and by theory. And as time goes on, many questions that weren't asked or were asked in a rather naive way become scientific because of new knowledge. So there are many questions, wonderful questions, that were asked when I was a graduate student. What is the atom? What is the nucleus made out of? How does it work? Those questions were answered by now. But they gave rise to new questions, many of which, in fact, most of which are not yet answered, but they are scientific questions that are well formulated. They will be answered. And it is that ignorance, those questions, that are the driving force of science. Those are the questions that you are going to be faced. So I like not to talk as much about what we know, the answers, which are crucial, that's what we build on, but rather the questions. And I give a talk like this often, where I list many questions that might guide physics, fundamental physics, over the long term. The long term in science is 25 years, is very long. Physics is a very basic part of our description of nature. It sort of underlies all in our reductionist understanding of the nature of physical reality. Physics is at the bottom, in a sense. And physicists do all sorts of things. And the questions I will discuss will range all the way from cosmology and astrophysics, the behavior of objects within the universe, and indeed the universe as a whole, to the behavior of ordinary materials or new materials we create, to the structure of elementary particles, to speculation about new physics at unbelievably high energies or short distances, to biology, There's no division in the real world between questions that are in the realm of biology and questions that are in the realm of physics. They're simply phenomena. And there are many of the most interesting questions that nature poses to us today are to be found in what we call interdisciplinary areas, which simply means that they're of interest to people who come from the different disciplines with different cultures, with different tools. And it is often those problems that are the most interesting. And biology is a good example of a science which is young, but developing extraordinarily rapidly and revealing new data, new phenomena that call out for explanation and have attracted not just, of course, biologists, but physicists as well. I don't really have time to go through 25 questions, so I'll go through about 15 or so. And let's start at the beginning, with the universe and its beginning. We have learned, as I said, an incredible amount about the universe. We think that the universe began somehow 13.7 billion years ago. It's quite remarkable. We now have measured the age of the universe to 1%. It's about, in your case, to a few months. So we know how old the universe is. We think it went through a period of rapid inflationary expansion and then settled down to a constant expansion. We have a picture of the universe when it was rather young, 300,000 years old. That was the point where the hot fireball expanded enough to cool down to a temperature that was low enough that electrons could attach themselves to nuclei and form neutral atoms. Before that, light couldn't go very far in the ionized plasma of the hot fireball. But after that, light flowed freely, and we still see it. We can take pictures of the light coming from the universe as it looked like 13.5 billion years ago. And this is the picture that was revealed in the first observation of the so-called microwave background radiation, because this radiation of light is peaked towards the microwave. It looks pretty boring. The universe has no structure, looks homogeneous, isotropic in all directions. It emits light over a wide range of spectra, and it fits beautifully a curve, which I'm sure many of you know is the Planck spectrum, predicted by Max Planck at the birth of quantum mechanics, that a black body radiates and is totally determined by its temperature. This, in fact, the universe 13.5 billion years ago is the best black body we have ever observed. This is the most accurate black body spectrum ever observed. This was observed by the Kobe satellite experiment, for which the principal leaders received the Nobel Prize 2 or 3 years ago. The temperature of the universe at that time was I forget exactly, but tens of millions of degrees Kelvin. Since then, the universe has expanded, and when you take a gas in a box, as you know, and you let the volume get bigger, the gas cools off. The temperature of that radiation we see today is 2.75 degrees Kelvin, accurately measured to 0.1%. Quite remarkable. So the universe was kind of boring. Isotropic, looks the same in all directions, but very puzzling, because if it was truly uniform like this, nothing would ever have happened. It would remain uniform. What's to cause a change? And certainly the universe we see when we walk out at night is not uniform. There are stars, there are galaxies. So we sort of knew that there had to be fluctuations, and the COBE satellite was the first to observe variations of this uniform gas of 1 part in 10,000. Very difficult to do. Little temperature variations of 1 part in 10,000, and those are the maps that you often see. This is the map from a successor experiment called WMAP, and there's another experiment which is up there taking data right now, which we will hear about in about a year, which should tell us a lot about the earliest history of the universe. And here the variations have been greatly exaggerated, but these little fluctuations come from fluctuations in the density of matter and radiation across the universe, and they are what should emerge, should be pulled together under the force of gravity and eventually form stars and galaxies. And one of the great successes of astrophysics in the last 20 years has been to measure in great detail this initial condition for the small little ripples in the universe and to understand how they became galaxies and the structure of the filaments which fill our universe. So we understand in extraordinary detail compared to 100 years ago, and there's much more to come, of this detailed history of the emergence of the structure that we see at night, structure of stars and galaxies, and their evolution over this last 13 billion years. We've discovered recently that there is something called dark energy, which I'll discuss later, in the universe, which makes the future of the universe a little uncertain. The universe, because of this energy, is accelerating rapidly, and we don't know whether that will continue. So we're not rather sure about what will happen in the future, and we're even less sure about what happened at the beginning, the so-called Big Bang, where all of our equations break down. So coming back to my question, the first question is, how did the universe begin? This is an interesting issue. Is it a scientific question? Can we experimentally, observationally probe back to the beginning or close to the beginning to test whatever crazy ideas theorists like me or others come up with? Well, we hope to. Not with light, because light can't get through this ionized plasma of the fireball. But gravity waves can. And the Planck mission that is the successor to COBE, which measures the cosmic microwave background, will be looking for signs of gravitational waves that came from very early on in the history of the universe. But can we answer a question like, how did the universe begin? That's like having a theory not of what happens once you're given an initial condition, the universe, but a theory of the initial condition. That's a rather new kind of question for physics. It's a question that people have been asking forever, answering with religion, philosophy, but now is a scientific question. And there are very interesting ideas about this, which I don't have time to discuss. But it's a very new kind of question and a fundamental challenge to physics. Can we imagine a theory of the initial condition? And what is it? People find it very hard to imagine a theory which would explain how time began. Maybe it didn't begin. Maybe the universe went through contractions, was cyclic. There are such speculations and ways of testing them. More likely, in my opinion, our changing notions of time itself and space and time will probably answer this question. And I do believe it will be answered, probably in your lifetime, maybe not mine, because it is now a scientific question, and scientific questions, once well formulated, amazingly enough, get answered very quickly in human scale, within human lifetimes. Okay, let's go on to what the universe is made out of. I'm not sure we need the lights on the screen. So you could have the lights on me. That light could be on. The universe, remarkably, we have discovered, and this is, as you know, very recent, within the last 20 years, it has become clear that most of the universe is not made out of the stuff that we are made out of, which was what everybody thought 20 years ago. The universe was made out of baryons, protons, electrons. We've discovered that even among the matter, the baryons, the matter in the universe, particles that have certain masses, most of the matter is not ordinary matter, but something we call dark matter. A matter that we've never directly seen in the laboratory or produced. And even then, that doesn't account for all the energy content of the universe. If you just count all the energy in the universe, most of it, 75%, is in something called dark energy. So this amazing discovery by astrophysicists and astronomers has posed deep problems for fundamental physics. What is dark matter, and what is dark energy? Dark matter is the problem the question that I think will be answered most quickly, probably within this decade. The evidence comes from astronomy. Turns out that in galaxies like ours, you have to add a lot of dark matter, matter that you cannot see. That's why it's called dark. Presumably, we think, made up of heavy particles that simply don't emit electromagnetic radiation, so we can't see them, and don't interact strongly with ordinary particles, because then we would see their effects. But everything that has energy, mass, will attract other bodies. That's the universal law of gravity. So this dark matter was observed indirectly in one way by seeing that it helps to pull the stars in orbits around galaxies, and without the dark matter, you would have to conclude that Newton's theory of gravity and Einstein's theory of gravity were wrong, because calculate the orbits using just the matter you see visible matter, you get the wrong answer. That's where dark matter, the observation came from, indirectly at first. But later, we learned other ways of observing dark matter. In Einstein's theory, if you have matter and light passes by, it is pulled towards the matter. Einstein, in fact, tells us that the matter, a star, for example, will curve space, and anything moving in that space will appear to have a deflected trajectory. So matter behaves like a lens, and you can detect its presence even if you can't see the matter by its distortion of the visual field. This is a very dramatic picture of two galaxies that have collided. And the red is the X-ray emission from the hot gas that is present in those galaxies. Whereas the blue stuff is the dark matter inferred by the distortion of these very bright objects that are behind the galaxy. From the distortion, you see some strange shapes here, elongated lines, which are distorted visions of point-like objects that are being seen through the dark matter. There's much more dark matter when you add up the mass than there is gas. The other interesting thing about the picture is this describes what happened about 1 billion years after two galaxies collide. They pass through each other. The gas interacts strongly with itself. There's friction, and it is dragged behind, whereas the dark matter, you see, is more spherical, just passes through. In a few billion years from now, these galaxies will have moved farther apart, and the gas will have fallen into the center of these halos. Anyway, that's the explanation, and this kind of picture is easily reproduced by calculation, just using essentially Newton's theory of gravity, and assuming there is this dark matter. So this is the visible matter, and this is the inferred dark matter. But what is it made out of? And can we see it? It's passing through you right now. Hundreds of dark matter particles are going through your bodies. And you don't feel a thing. And that's the problem. You see, if you did feel something, one of these impacts, dark matter interacted with one of your ordinary quarks or electron, then you would detect dark matter. It happens very rarely, so that this kind of radiation, this kind of bombardment doesn't hurt you, but also it means it's very hard to detect. You need to build very sensitive instruments and put them very far underground and wait a long time. But we're just at the stage where many of us think that we will see the dark matter wind sometime the next 10 years, maybe next year. The other thing we can do is produce it. Any kind of matter can be produced, sometimes with its antimatter in the laboratory if you have enough energy. These dark matter particles probably weigh 200,000 times more than the proton. But in high-energy particle accelerators, we can produce particles that weigh that much, and do, and we hope to at the Large Hadron Collider, which is now beginning to operate in Geneva. So this is a marvelous question, and one that will tell us what most of the matter in the universe is, and probably do so in the next decade. Dark energy is a different kind of problem. It is hard to detect unless you look at the universe as a whole. It's sort of unfortunate, you know, most of the energy in the universe is in the form of this dark energy, which is everywhere. It's very dilute. There's very little per cubic meter, but when you add it up over the whole universe, most of which is empty, it's a lot. We can't use it, unfortunately, to solve the energy problem. We can't even see any effects that it has unless we look at the universe as a whole, where it is responsible for this expansion of the universe to go faster and faster, to accelerate. We believe, at least I believe, many, that this is simply what Einstein realized, part of his theory called the cosmological constant. If it is really such a constant and a permanent feature of our universe, then this accelerated expansion will go on forever. It will be the it is already now 75% of the energy of the universe, but in 15 billion years from now, double the age of the universe, it will be 95% of the energy of the universe. It is a constant. It doesn't dilute. And the universe will accelerate even faster. It will be what determines the end of the universe, which is as interesting a question as the beginning. Einstein's cosmological constant has a long and checkered history, but it is simply the energy of the vacuum. So when we add up various forms of energy, we have, of course, ordinary mass, ordinary matter, E equals mc squared, which carries energy even at rest. We have kinetic energy due to motion. And we have the energy of the vacuum. If you take away all the matter, you still could have energy in the vacuum. And in fact, we believe have to. It is a remarkable kind of energy. Most kinds of energy look different to different observers. For example, your energy is just your rest energy because you're sitting at rest relative to me. So I say your energy is your mass, I would say 60 kilograms, times c squared. But if I start running away from you, then you look like you're running away from me. So you have, in addition, kinetic energy. So your energy depends on the observer. This kind of energy better not depend on the observer. Otherwise, there would be an ether. There would be a preferred observer. Einstein's cosmological energy is the only possible form of energy and pressure, a kind of gas with energy and pressure which looks the same to all observers, doesn't pick out a preferred frame. A consequence of that is that if there's energy, there's also pressure, and the pressure is negative. It's not like a gas pushing out on the walls of a box, but rather pulling in. It's like negative mass or negative energy if it was energy. Energy is always positive, but pressure can be negative. It is the negative pressure of this gas that behaves like anti-gravity and makes the universe expand faster and faster. We, in fact, those measurements of the acceleration of the universe have determined that not only is there negative energy, there's there's also negative pressure, just like Einstein's theory naturally predicts. So that's probably what it is. That's the only form of energy and pressure consistent with there being no preferred observer, consistent with Einstein's basic principle of general relativity. And as I said, it causes this accelerated expansion which gets worse and worse as time goes on. Where does it come from? How can I say, how can nothing, the vacuum, have energy? What does it mean? Well, I want to tell you a bit about the vacuum, which is where we live. So the vacuum is most normally thought to be a pretty boring subject because there's nothing there. You've removed all matter, turned off all fields. There's just empty vacuum. But in quantum mechanics, the vacuum is very interesting and complicated. Because in quantum mechanics, we learned that any dynamical variable, an oscillating pendulum, can't be truly at rest or turned off or not present. There are always quantum fluctuations. If you want the very act of observing a quantum object sets it in motion, the uncertainty principle. The very act of observing a vacuum in a quantum mechanical system creates fluctuations. And so whereas the classical vacuum might be empty and boring, the quantum vacuum actually looks something like this. So this is a calculation of fluctuating fields, chromodynamic fields that hold quarks together in the vacuum. The distance here, the distances here are about the size of a proton. So about 4 protons fit into this picture. And this is a calculation that shows you how the chromodynamic fields fluctuate in the vacuum according to quantum chromodynamics. In addition to the fields, there were these little particles that you saw come in to being and disappear, these virtual particles. Again, particle-antiparticle pairs can appear momentarily and disappear in the quantum mechanical description of nature. Because of that, the vacuum should not be thought of as just nothing, the ground state, the state with no motion, but rather more like a complicated medium. You don't see this in the vacuum, in an ordinary vacuum tube, because you're not looking at distances of order 10 to the minus 13 centimeters. So if you do, as we do in high energy collisions, you do probe and measure and check the properties of the quantum vacuum at these scales. Well, this gives rise to remarkable effects all throughout fundamental physics. And now a bit about my own work. It was our understanding of the quantum mechanical properties of a generalization of electromagnetism that explains some of the most mysterious properties of quarks, a phenomena called asymptotic freedom. See, the vacuum is kind of a dielectric medium, except that it's the opposite of a dielectric medium. Dielectric mediums screen the force between charged particles and make it weaker as you separate the particles. What we discovered was that in a version of electromagnetism where there are three kinds of charges, we call them colors for objects like quarks, the quantum vacuum behaves in the opposite way, and the force between quarks gets weaker when they're close together and stronger when they're far apart. That could explain, did explain, and eventually in highly quantitative way, experiments done on quarks at very short distance that really proved that they made up the proton, but also explained why you could never pull them out of a proton. Well, they're permanently confined because they get a stronger and stronger force when you pull them apart. This phenomena of asymptotic freedom led us to this theory, quantum chromodynamics, the quantum theory of the nuclear force, which is based on objects which carry charge, three kinds of charges, we call them colors, red, white, and blue, held together by fields, chromodynamic fields, just like in electromagnetism, except with three charges and this very strange quantum vacuum. So a bit about the Nobel Prize. This is a description in the theory of what happens when you pull these quarks apart. In effect, the quantum vacuum pushes the flux lines together. So in the case of electromagnetism, the flux lines of the electric field are determined by Coulomb's law. They spread out. In the quantum vacuum, quantum chromodynamics, the medium doesn't like to have flux flowing through it, so it pushes these flux lines together, and you get this flux tube, which confines the quarks forever. So if you get a Nobel Prize, you get to go to, as Dr. Ernst showed you, to Sweden and have a wonderful time. And I actually did sit next to the, I also sat next to the Queen. And this is the Crown Prince. This is a few years later. They're a little older. And you also get a prize, and you get a medal, and you get a check. But most, in a way, the nicest thing you get is a beautiful diploma. And the diploma has an original work of art drawn by a Swedish artist, in this case depicting three quarks inside the nucleus, right? Trying to get out, if you want, but confined by this weird force which is produced by the quantum vacuum. And they also make a poster. There's a cute poster they made about this prize, where you see a picture of three quarks trying to get out of the proton, but unable to do so. Except they got the picture wrong. You see, they have it like a triangle. You see the flux going here and here and here. It's not obvious how the flux goes when you have three quarks. When you have two, there's a tube. But what do you do when you have three? Well, they guessed this, I guess. But here's how it really works. Again, you calculate what happens if you try to pull three quarks out of the proton. Well, this is what happens according to the theory. The flux is confined, you see, to these three tubes, but it's not a triangle, it's more like a triad. Doesn't matter, they got everything else correct. Now, this fluctuating fields in the vacuum look like they have a lot of energy, right? And that's right, they do. these fluctuations of anything that can exist in the vacuum, particles and antiparticles and fields, give rise to an enormous energy. And a back-of-the-envelope calculation gives a number, forget about the units, but it's a big number, 10 to the 120. The cosmological constant that's measured is 10 to the minus 4 in the same units. That's not very good when you do a back-of-the-envelope calculation and you're off by 124 orders of magnitude. It's not so bad. We've encountered such problems before many times in physics. I can think of at least 4 examples where within the last 50 years we have come up with answers to numbers which are exceedingly small for a good reason. The problem with the cosmological constant, the mystery of dark energy, is not what it is. It probably is Einstein's cosmological constant, the vacuum energy. Our problem is this very small number. Why? We don't understand qualitatively why it's so small. That doesn't mean that we won't. We, or more likely you, will figure it out. But at the moment, it is a fundamental, perhaps the most fundamental challenge for physics, for theoretical fundamental physics, to understand this very small number that governs the structure of the universe. So I'm running out of time rapidly. I'll move from cosmology to particle physics, where we have this incredible theory called the Standard Model, based on identifying the 3 families of quarks and leptons that make up all the matter we've ever observed. Up and down quarks that make up nucleons, electrons, and neutrinos, and 2 other similar families, heavier, we don't understand why, with a mix in ways that we can measure but don't understand why. What we do understand in great detail are the 3 forces that act. Electromagnetism, the strong nuclear force, and the weak nuclear force. But there are many, many questions, even in this theory, which works so much better than any theory in physics has ever worked. It has been tested. Its fundamental principles and features have been tested in literally thousands of experiments with unbelievable precision, and we see no barrier until we get to extraordinarily short distances. We also know from observation and measurement that it works in describing objects throughout the galaxy. It works from the edge of the universe to the shortest imaginable distances. And yet there's so many questions. We don't understand where the values and pattern of masses of quarks and leptons. It's a very strange spectrum. We can't see rhyme or reason. We can't certainly calculate. The universe, as you know, is made up of matter with very little antimatter. We understand how that can come about, partially due to the work of Kobayashi and Masukawa and the discovery of CP violation. There are mechanisms that could produce matter without producing antimatter, but baryons, which we would like to calculate, understand the amount of matter that exists in our observable universe. We still don't. There are other particles we think exist but haven't yet detected. And perhaps the major question is these forces, the forces of nature. There are 4 forces we've identified in nature: gravity, these atomic forces, the strong and the weak, and electromagnetism. They're all at the core very similar. The whole picture cries out for unification. All the particles we've discovered, the elementary constituents of matter, fit together like pieces of a jigsaw puzzle? Can we unify all the forces? We probably have to, we are convinced, to answer some of these questions and many, many other questions that cannot yet be answered by the Standard Model. And so we try to unifor. Now, asymptotic freedom helps because the strong force is so much stronger than the other forces that unless it was for this phenomena that it gets weaker and weaker, you'd never think that it could be unified with the very much weaker force of electromagnetism. But if you take into account this weakening and extrapolate to very high energies corresponding to very short distances, then the strong force and the electromagnetic force and the weak force become the same. This is one of the most important clues we have from experiment, which measures these forces, and theory, which allows us to extrapolate, that the unification works, fits, everything seems to fit, and it occurs at an extraordinarily high energy. 1,000,000,000,000 million times higher than our present accelerators. It's actually the energy at which gravity becomes a strong force. Gravity, as you know, is a weak force. When you do chemistry or atomic physics or nuclear physics, you don't have to worry about gravity. It's weaker than the electric force in the atom by 1 part in 10 to the 40. We only feel it because there's no anti-gravity. It cannot be shielded. It adds up. So I can hold this up. I'm exerting a little bit of electric force, and the whole Earth is pulling down on it. That's 10 to the 50 atoms are pulling on this. And I hold it up with just a little bit of electrical chemical force. But gravity, the charge of gravity, the source of the gravitational field is mass. Mass is energy. So at high energies, the force of gravity increases quadratically. And at these energies of unification of the atomic and nuclear forces, gravity is equally important. That's a very strong clue that the next unification, the next big unification of physics, which tends to make progress at the fundamental level by unifying electricity, magnets, other forces together, will include gravity. And gravity is a very interesting and different kind of force. Hard to bring into the picture. One of the reasons it's led us to a rather dramatic, different approach to fundamental physics, originally based on the idea that you don't really have elementary particles at all. You have vibrating strings. They only look like point particles at large distances. And in such a theory, one can in fact naturally, easily, inevitably unify all these kinds of forces together with gravity. Takes us to the next important question, which I don't have time to discuss, but just to pose, is this approach correct? Is it true that all these particles are just different vibrations of a superstring? String theory has had some enormous successes. It still has enormous problems. It's still in development. It's really not yet a theory. But it has, in my opinion, enormous promise. And it raises questions, it and the existence of quantum mechanics and gravity in general, raise profound questions, once again, about space and time. Space and time are the most fundamental concepts that we acquire as infants as we try to walk about the way to describe and understand physical reality. And over the centuries, we've had to change our notions about space-time, especially in the last century with special relativity and then general relativity, when Einstein taught us that space and time are dynamical and can bend and curve, and that's the origin of gravity. And now, once again, we're asking profound new questions about space and time. For example, are there more than 3 dimensions? There could very well be more than 3 dimensions. If an extra dimension, x, y, z, and another one is very small, curled up, you wouldn't notice it unless you have a microscope powerful enough to see such distances. And the distances we're talking about are a million, billion times smaller than our most powerful microscopes. In string theory, for example, we're forced, we calculate how many dimensions there are, and there's 6 more in many versions. And as if in each point in space there's a little space, a little extra 6 directions you could go, which are all curled up into beautiful structures. And in fact, it's the shape of these hidden dimensions that, in these models, determine the nature of the forces that we see, the form of matter, their masses, their mixings, everything we can't yet answer. So we have this framework which can do this. It has many solutions. In fact, too many solutions. We don't yet know what is missing in this framework that would determine and predict, post-stick, what we've already measured and predict the results of new measurements. We have other hints, even independent of string theory, that space also has a different kind of dimension, a quantum dimension. These are dimensions of space-time which are not measured with ordinary numbers that commute, but rather quantum dimensions that anti-commute. It's called supersymmetry. And this is something we have many clues might exist as a fundamental symmetry of super space-time. And it has a chance, it makes many predictions about stuff that will be explored at the LHC. So here again, we're in a very good position because we have the right microscope. The Large Hadron Collider runs between Switzerland and France, an immense, expensive, heroic undertaking of science and technology. This is the tunnel, the magnets that hold the beams in place as the protons run around, collide at energies of close to 10 trillion electron volts. The results of those collisions are seen in enormous detectors like this. This is the CMS detector. This is the Atlas detector. This is a person. These are toroidal magnets. These are truly achievements of mankind that easily surpass, in my opinion, the pyramids. And they're better than the pyramids. The pyramids are beautiful. They were monuments to the hereafter and to God, to the gods of the Egyptians. These are monuments to science and to the exploration of new knowledge. A year ago, the LHC started taking data, and this is an illustration of the CMS detector, which has many, many layers of this enormous detector. A collision takes place. Hundreds of particles come out. They're all measured. And then the experimentalists accumulate terabytes of data and analyze literally billions of collisions, hundreds of billions of collisions, in order to find interesting stuff, events like this. But what I'm really hoping for, oh, I missed it. Anyway, Events like this that could discover the superworld. Signs of new particles. Most important new particle we would hope to see here is the dark matter particle. Supersymmetry actually tells us that there probably would be a dark matter particle seen here, but we don't know. But this is the right energy range to produce that dark matter particle, as well as particles predicted by supersymmetry. This superworld, which would be an immensely revolutionary discovery. It would be tantamount to discovering that space-time has these extra quantum dimensions. Our picture of physical reality would then require that we truly think, our picture of physical reality would be that events and processes take place not in space-time, but in super space-time. And even more than that, in string theory and in quantum gravity, we are beginning to wonder about what space-time is really. We have all sorts of clues, theoretical clues, no observational experimental clues, but theoretical clues, which are good, that space-time is probably a bad fundamental concept, that it is better thought of as an emergent concept, an approximation to the description of physical reality for large objects in certain circumstances. Most of what we've encountered so far, of course, but in the end, we would like to understand, if you want, what space and time are made out of. This is speculative, but real, strong clues that we might have to alter our notions of space and time. So I'm really running out of time. I'm just going to run very fast through a few questions outside of the fundamental areas of cosmology and particle physics to ordinary materials that we see around us. We are now beginning in field of so-called condensed matter physics to explore in a very exciting way totally new materials. We, of course, have all heard of last year's Nobel Prize for the beautiful construction of a new material, a two-dimensional film of carbon with this hexagonal lattice, graphene, which has marvelous properties of great interest both for just fundamental science and for technology. But in addition, we are acquiring over a very broad spectrum of areas unbelievable control over ordinary and new materials at the level of atoms, with the ability to manipulate these structures atom by atom, construct new materials, or explore physics at the atomic level in detail. This is an example of being able to create materials at will and vary their properties in the laboratory by trapping individual atoms in an optical lattice after being cooled to incredibly low temperatures. So you can create a lattice of atoms, adjust their positions cleverly with lasers and magnetic fields, adjust the interactions between the atoms. For theorists like me, this is an incredible advance because we can ask our experimental friends to construct for us model theories in the laboratory, which we have been playing around with pencil and paper for many years, and to test and learn about the behavior of materials and collections of atoms at the atomic level. This is where one can simulate and observe in these cold atom systems phase transitions between superfluids and insulators. Amazing field. Being able to construct and construct new kinds of materials or control atoms at the quantum level has given rise to a goal which will be around in your lifetime for quite a while, I believe, but a wonderful goal of constructing a quantum computer. Not a computer based on classical bits, zeros and ones, like all of the computers we use today, but one based on this word here is quantum. This is classical. This should be quantum. The quantum bits are made out of little spins. An electron has a spin up, spin down. You could use those two states just like you use 0, 1, 0, 1 to construct binary numbers and do calculations and run a computer. But in a quantum bit, in addition to spin up or spin down, you can construct a superposition of spin up, spin down. So a quantum computer made up out of spins has a much larger space in which the bits live. And it can do things that a classical computer can't do easily. For example, it turns out it can factor large numbers very fast. Whereas large computers can't. That's why the security system in your internet is all based on factoring large numbers. So you send large numbers, and somebody has a key. It works if nobody can factor large numbers fast. A quantum computer would destroy the security of all internet communication, which is paradoxically why the governments are pouring so much money into constructing a quantum computer. But it's not easy to construct a quantum computer, just like it's not easy to experimentally test Schrödinger's cat. Because the environment decoheres. The interaction of the environment decoheres these quantum states, if you want, does a measurement on each bit and makes it a classical bit. The search for the ability to control individual atoms or construct new materials with topological states that could be robust against such decoherence is pushing an incredible amount of fascinating basic science, which will be of great interest and importance even if we never develop a quantum computer. Finally, I'll end with a few remarks about biology. As I said, biology, there are many, many questions in what I call living matter, which physicists have become fascinated with. There's an incredible amount of data, the problems are wonderful, and many physicists believe that they can bring the incredible power of physics to do quantitative modeling and deal with complex systems to bear. This is an increasing avenue, indeed, for physics. At my Institute of Theoretical Physics in Santa Barbara, where we run programs, thousands of visitors a year, about now 1/6 of our programs are on really biology or the physics of living matter. The kinds of things that theorists in physics get interested in are general principles of biology, a theory of biology. That has a dirty name in biology by and large, but the climate is changing. And we think we can help. Maybe developing new kinds of mathematical tools. One area is genomics. We have a program right now running at the KITP on evolutionary modeling of viral and bacterial populations. You can actually do experiments easily. Viruses reproduce so rapidly, you can do experiments in the laboratory in real time and test these models. But can you make evolutionary theory quantitative and predictive, or is it just accidental, happen once, and that's it? I like to pose in this way. Can you tell the shape of an organism by looking at the genome? The genome has an incredible amount of information in it, which we're trying to decode. Imagine in about 100 years from now, Theoretical Genomics 101, this is the final exam. Based on this genetic sequence, draw a picture of the organism. And the answer is this. Another area where physicists, many, are trying to make contributions to biology is neuroscience, where it has always been clear that you need modelers or theorists even to collect the data. The data is just too complex and too abstract to understand how the brain works. It's just a bunch of electrical signals. To understand how the brain works, you have to model and understand that data. The kinds of questions many theorists come from physics ask in this field are, what are the principles, not just the detailed phenomena of each, but the principles that underlie the kind of self-organization that's required for memory and consciousness. Consciousness, by and large, is something neuroscientists only recently have dared to even start talking about. It's a complicated phenomena. Here is the kind of question a physicist might ask, and in fact, I stole this from a physicist who did ask this question. Oh, this was one question. Can one make a machine with free will? It's very interesting. One aspect of consciousness that we all believe is correct is that we have free will. If, as most of us believe, consciousness is just a property of a physical system, we might be able to therefore create a machine with free will and do experiments on it. And this question is one I particularly like. Can one measure the onset of consciousness in an infant? This actually came from a theoretical condensed matter physicist, Phil Anderson, also a Nobel laureate, who's interested in these issues. The question is not what is consciousness. That's a sort of philosophical question. The question is, can one measure the onset of consciousness? And what I mean by that is, if we draw a plot of consciousness versus age, it's clear that an embryo, to be safe, doesn't have consciousness, whereas a teenager is conscious, right? Somewhere in between, there is a transition. And in physics, we've learned that you can learn a lot about a complicated system which has different phases by concentrating on the transition between those phases. So is there a transition, and how can one measure it? Is it discontinuous? Is it continuous? And how can you measure it? And you can measure things often without actually understanding them. If you find something that correlates with the different phases, and you can measure them in different species. It's a great question, and perhaps a different kind of question than biologists often ask. So I'm over. I've gone a long time over, ignoring my polite hosts. I'm just going to pose the last question, to which I know the answer. And I hope you know the answer. Will physics continue to be important? And the answer is yes. Thank you.
Thank you very much, Dr. Krauss. Now I would like to give a microphone to Dr. Koji Hashimoto, Associate Chief Scientist